So in this video we're going to be talking about how to wire up these cheap Chinese servo drivers, how I've done this with my breakout board, and the pros and cons of using some cheap Chinese servo drivers. Stick around. So this is a very Chinese manual that comes with your servo drivers. There is an English translated manual out there. The English translated manual isn't very useful. I can't vouch on how useful the Chinese one is if you can read Chinese, but I can't. So essentially, if you want to connect this up, if you want to use the pulse and direction aspect of these drives, because you could also run or command them using 0 to 10 volts. But in this instance, or this topic of this video is just going to be pulse and direction. So if you want to command it with pulse and direction, if you look at the overview schematic, it's going to be this part of the circuit. So this over here. So the pins that we'll probably be interested in are 3, 14, 4 and 5. So there's multiple ways of commanding the pulse and direction signals. The manual recommends a differential circuit. So I'll go on to that in a little bit. You can also run a 24 volt single-ended input into these pulse and direction signals. For that you actually need a common collector, so you effectively have to pull 14 and I think that's 5 over here. You need to pull those to ground, and that allows the 24 volts to flow into the optocoupler and then flow back out into ground, effectively completing that circuit. So you need to have some sort of transistor or maybe a MOSFET to actually do that for you. Most breakout boards though, or most common interfacing, especially in the hobbyist environment, is just simply a single-ended 5 volt circuit. So that's not actually listed over here, but that's easy enough because essentially inside that your servo driver, it uses the same optocoupler for this and this circuit, and then you have access to all of these pins, so you can actually use this part and you can still run it in a single-ended 5 volt circuit. So how would you do that? It's actually really simple. You'd have pins 3, 14, 4 and 5, and you would have your signal coming in into 3, and then that will be your 5 volt signal. So that would be, in this instance, that would be your pulse. Your pulse signal coming into 3, and then your 14 would be connected to ground. So we connect 14 to ground. And then we also connect 5 to ground. It's quite a poorly drawn diagram here. But well, demonstrates the point. Anyway, so you'd have your 5 volt signal for direction coming into 4. So essentially, if you are going to run your circuit like this, you need to be mindful of noise. You need to make sure that your pulses are well-defined square waves. You also need to ensure that you're not running this in a noisy environment. Essentially, the manual does not recommend running a single-ended 5 volt circuit. It doesn't even give you an option to do it. And I can't vouch for how well this works because I haven't done this myself, but I do know that is possible. The manual recommends using a 24 volt single-ended circuit because it increases the signal to noise ratio. By using a differential circuit, you also have common mode noise immunity. So I urge you to maybe watch some videos on that. But essentially, by using a differential circuit, which is preferred by the manual, you can also run your inputs into the servo drive slightly faster, or so it says, so up to 550 kilohertz opposed to 200 kilohertz if you're only using this circuit. The actual servo driver doesn't use a differential line receiver, so I think some of the benefits from using a differential circuit is maybe lost. But nevertheless, it is the recommended way, and it's how I'm commanding these servos currently. So it'll be interesting to know in the comments maybe some links to the benefits and disadvantages of using a differential line receiver and an optocoupler in this situation. My understanding is an optocoupler doesn't give you the same level of noise immunity that you would otherwise get for a differential line receiver. But I understand that in this application, the reason why they've used an optocoupler is that they can use the same optocoupler for both sides of the circuit, so both single-ended and the differential side of the circuit. So how would you connect it up with differential? And I suggest you do so because this is the preferred method and also opens the doors to higher frequencies. So running it in a differential mode requires the use of a line driver, which is easily found. It's relatively cheap and it's quite easy to connect up. So you might need to make a PCB. Alternatively, you can actually just wire solder things to the pin, maybe get a perf board. That's how I made my first initial circuits. It's actually not very difficult. The reason why you might want to run a high frequency though is because you can effectively use the servo drivers to their maximum capabilities. The servo drivers have electronic gearing. I can go into that in a little bit. But essentially, by commanding a higher frequency for the stock settings, you have access to higher speeds from the actual driver. So you can effectively run it at its maximum commanded velocity speeds, or this maximum RPM, for example. So if we were to use a differential line driver, you could purchase AM. So an AM 26LS31. These are the line drivers that I'm using, and they work relatively well in this application. So effectively on your circuit, you have these pins. So all you need to do is you need to connect VCC to a 5-volt source. So let's call that 5-volt set. And then it recommends using a capacitor. So you use a bypass capacitor, or it's effectively a filtering capacitor at the input to filter any unwanted noise in, say, your power supply or your input voltage, so your 5 volts coming in. And you connect your actual ground wire. So I'll show you in a bit. So ground is connected to ground. So that's effectively 0 volts. So ground. And then we connect that ground wire over there to these pins up here. So that there is connected to ground. Ground is connected. VCC comes in. So 1A, which is over here, this becomes your input. So your 5 volts single-ended circuit. So the 5 volts coming from, say, your breakout board, or say a 5-volt single-ended circuit coming from your motion controller, or even your parallel port, would come in to A. And then Y over here, this gets connected directly to pin number 4. Pin number 4. Z gets connected directly to pin number 5. And then you've got 2Z over here. That's 14. Then this is 3. And then 2A, that's going to be your input again. So your 5 volt over here, that is going to be your 5 volt. I believe that's direction. So let me just double check. Yep, so that's the direction signal. That one there. And then this circuit, so 2A, is connected to your pulse circuit. So your pulse coming through. So that's five volts pulse. So essentially 5, 14, 13, and so 5, 4, 5, 14, and 3 are these pins over here. So these pins over here, 3, 14, 4, and 5. So connect them directly up to that. And then you effectively have a little circuit that's able to convert single-ended circuits, or single-ended 5-volt circuits, single-ended 5-volt signals into differential signals that is able to communicate with your servo drivers. So you also have inputs and outputs into the drive, and they're super easy to set up. So effectively for your inputs, it's just a switch. You can run it through, say, a relay, or you can run it through maybe a transistor or a MOSFET, whichever is convenient for you. All you have to do though is connect 6, 7, 21 and 8 to ground. You just need to connect those to 10. So give 9, so pin number 9, you got to feed it 12 to 24 volts, and then 10 is your common, so that is also on the actual diagram itself. So let me go a couple of pages ahead. So number 9 is connected to 12 to 24 volts, and then 10 over here, that's connected to common, so 0 volts, and then all you have to do is you need to connect 6 to ground, so or 7 to ground, whichever signal you want. So by default, signal in number 1, 6, is a servo enable. It turns the servo on. You can just turn that off. You can change the parameters on the servo drive, and then that fixes that problem, so the servos are effectively always on. Or what you could do, if you want to use a default setting and you don't want to change anything, all you have to do is connect 6, pin number 6 to 10, and then feed in 12 24 volts on 9, and then connect 10 to common. So I've got like a little connector over here. It's quite a dodgy one, I've been soldering into it previously, but effectively on here, pin number 1's up here, pin 25 is on this right hand bottom corner, and then 13's over here. So 9 would be, so 9, which is over here, that would be somewhere around here. That would be connected to 24 volts, or 12 to 24 volts. 10 just below it would be connected to 0 volts, and then you'd connect, say, 6, which is, I don't know, somewhere up here. You connect 6 all the way to 10, and then that will bypass that, and therefore your servo will always be on. The signal out is, again, just as easy. So your signal out is essentially, if I put that there, your signal out is essentially, you have to provide it with, so there's a Darlington pair inside the actual servo driver, which is part of the optocoupler. So all it really does is it connects anything coming in to ground. So it just shorts it effectively to ground. It's an open collector. So pins number 11, 23, 12 and 24, if you put, say, an optocoupler in between it and, say, a resistor in line, and connect it to your power source. So if I zoom in, so yeah, power source comes in, whatever that may well be, go through your optocoupler or whatever you're trying to connect, you know, using as your output of the servo driver, and then you connect it to those pins, and then effectively when the servo driver wants to give you an output, it shorts that to ground and then connects that to 10 volts, or to 0 volts, sorry. So this is a board that I've designed to actually connect my motion control board up to my servo drivers. The intention of this board actually is to really have a plug and play system. So I didn't really want a board in which I have to play around with the wires coming out and actually manipulate some of the wires to actually fit my servo drivers. This board also does certain aspects which I would otherwise not be able to get from, say, a standard board, and I'll go into that now. I've basically got all the features that I need for my application, and I've put it on a PCB. Essentially, at the heart of it, I've got the CNC drive motion control board. So this board itself is a UC300 ETH, so the Ethernet version of the CNC drive motion control board. It produces up to 400 kilohertz of an output square wave. It's 5 volt outputs and it's 5 volt inputs. It's also got an analog section over here which gives a 0 to 10 volt output and also receives a 0 to 10 volt analog input. So in essence, I've separated the board into distinct areas. So these areas over here are dedicated to my servo driver outputs and inputs. Over here I've got inputs, so these are inputs into, say, the motion control board. I've got an analog section over here. I've got an extended range of inputs over here, which so make part of my safety circuit as well, which is on board on this actual breakout board. I've got an output section over here, and then I've got safety circuit, relay, charge pump relay. I've got some monostable multi-vibrator circuits for pulse shaping and timing, and then I've got a 5 volt buck converter. So this converts the 12 to 24 volt input, it converts it down to 5 volts to actually operate the opto-isolated 5 volt side of the circuit. And then I also have the isolated 5 volts that comes in over here. So this powers the motion control board, and it also powers all the circuitry that's on the motion control side of things. So essentially what this board is doing is it's providing an interface between this board and all my connections that come into this breakout board, but it places an isolation, so it places optocouplers between each of these connections, and that helps isolate this part of the circuit from this motion control board. So if anything goes wrong and something happens and it blows, I don't know, something over here, that comes through, that voltage comes through, it doesn't make its way past, or the intention is it doesn't make its way past these optocouplers. So for the inputs, I've used some high-speed optocouplers. They're quite pricey, but they also have the rated speeds. Well, their rated speeds is far in excess of what I need them to be. These I think are rated to 10 megabits, so they're fast enough for our application. I've actually put 2 voltage levels on the inputs. So I've got some rated to 12 to 24 volts, and then I've got others rated to 5 volts. So the 5 volt circuit, for the 5 volt inputs, I can happily use them at 12 to 24 volts. I just need to put a resistor in line. But essentially, the whole row is dedicated to inputs. The inputs come along, they go through the optocoupler, they light up a blue LED, and then they go through a Schmitt inverter for noise immunity, or to improve the noise immunity, and that in turn gets fed into the optocoupler, the motion control board. I've got my analog circuits over here, so my analog inputs and outputs. These are not isolated. The reason why I haven't isolated them is because I'm probably not going to be using that. I've just put them there just in case if I want to use them in the future, I have access to them. But they're not isolated. They're the only part of the whole, or they're only part of the circuitry that isn't opto-isolated. I've got the optocouplers, which control the inputs into the servo drivers. So these are over here, and they're wired, I believe, the inputs into the servo drivers require just their open collector output, so these optocouplers effectively short them to ground. I've got some differential line drivers, so the differential line driver controls the pulse and the direction on the actual servo drivers, and that's isolated by these 2 optocouplers over here. I also have a differential line receiver, so the differential line receiver, the intention of that is to ensure that the encoders, or the encoders on the servo drivers, I maybe have the possibility of looking at what they're doing in the future. So that's going to be quite useful for, say, for example, tuning the actual motors. There's no actual output, there's no feedback from the actual servo drivers apart from this encoder count, or this encoder values, to actually know what the actual motors are doing. And therefore, by not actually knowing what the commanded velocity or the commanded motion profile looks like, you don't know whether you're overshooting or undershooting. You don't understand, or you can't understand the dynamic response that you're getting. So the intention is to actually have this differential line receiver talk to the encoders, and then that goes through some optocouplers. And then the idea is, in the future, I might be able to actually plot some of those graphs and actually have a look at what the motion profile is like. I've got the optocoupler over here, which interfaces to the outputs of the servo drivers, and then this over here is, I believe is just a Schmitt trigger, or actually it might be the other way around. That's a Schmitt trigger, and then that there is an optocoupler for the outputs. So the outputs, I believe, are blue over here. These over here are yellow. I believe the LEDs are yellow, the LEDs are blue. All the inputs that come in are blue. So on this side of the board, what I've done is I've dedicated this area to outputs. So these outputs are open collector outputs. So effectively, when you command an output, when you turn them on, it connects that pin up to ground. Each of the MOSFETs on here are rated to about 380 milliamps, which is sufficient for most of the things I'm going to use in my application. I've also got this area over here dedicated to inputs. This is a 5 volt input. This is also connected up to my onboard safety system, which I can talk about in a bit. This part, or these outputs over here, are also part of that safety system. Over here I've got two relays. So that relay there is just a dumb relay that's connected to one of the output pins on this motion control board. This relay over here is also connected to one of the output pins on this motion control board, but it's also connected to this monostable multivibrator. So the intention of these circuits, this circuitry over here, is to pulse shape or pulse, to alter the timing of some of the pulses that come out this motion control board. I'll talk about that in a bit. But essentially, one of these, or one of the sides of the monostable multivibrator, that's the one, sorry, apologies. The intention of that is to take the charge pump circuit and then look for that 12.5 kilohertz charge pump circuit, or signal, I should say. And then when it detects a 12.5 kilohertz signal, what it does is you have the option to turn on this relay. So you have the option to turn on this relay, or you can use this relay as just a dumb output from the actual motion control board. And in my instance, I can do that by just jumping this pin over here. So I can jump that pin, and then I have a choice of actually using that relay as a charge pump relay, or I can use it as just a normal relay. I've also got that charge pump output connected to this 5-volt output over here. So when that thing, or when the charge pump signal is actually present, the 5-volt output is also high. So I've got the monostable multivibrator circuit over here. The reason why I had to include this is because of the inherent nature of the things I'm connecting up. So essentially on my board I have these servo drivers, and I'm going to set the kernel speed to 400 kilohertz so I can get the most out of my actual servo drives themselves. But the problem is, if I run, say, my stepper drivers at 400 kilohertz, the pulse isn't long enough for the optocouplers and the stepper drivers to pick up on. So what do I mean by that? I mean, in very simple terms, if I draw it out, I have a square wave coming through at 400 kilohertz. It looks a bit like that. Probably looks a little bit better than that. I mean, I'm running out of ink here. Wow. But at 400 kilohertz, the actual width of this pulse, so the width of this pulse, I believe is 1.25 microseconds. That's not long enough to actually promote a bit change or promote a change in some of the optocouplers. Optocouplers are much slower optocouplers on the actual stepper drivers. So my circuit or my servo drivers may be commanding velocities that require a signal that comes in this fast, but my stepper drivers may be running at much slower speeds. They might be running in which the pulse looks a bit like this. But this over here, this isn't long enough for the optocouplers to pick up. So what this circuitry does over here, does, all it does is it extends this pulse. So this pulse, which may well be streaming in at 100 kilohertz, which is the maximum frequency that I actually can command my stepper motors at, that monostable multivibrator just extends that pulse. So that width there is just long enough for those optocouplers to see. So this monostable multivibrator that I've got connected on my circuit, the maximum frequency that you can put through that, I believe, is around 90 kilohertz. So it's fine for my application. And anything higher than that, effectively the output is always on, because it's a retriggable monostable multivibrator. That's quite a mouthful out. But yeah, so essentially that there controls some of the pulse timings on my output pins. I've isolated the ground planes on both sides, so you can just about pick it up maybe, but you can see that each of the actual circuitry are on their dedicated ground planes. So that's ensuring that both sides of the circuit are kept separate. So if anything does happen on any of these input pins or output pins, it doesn't affect this over here, or it shouldn't affect this over here. I also have a safety circuit over here. So the safety circuit, or the intention of the safety circuit, is to really connect some of the servo drivers and the outputs and input pins all in one. What it does is it basically in hardware looks at these input pins, and then it sees if any of the inputs go low. So it's an active low. If any of these inputs go low, then what it does is it triggers the safety circuit, and then it sends the outputs high, so it connects each of these outputs to ground, but it also sends a signal to each of the servo drivers to say, hey look, I've got a problem, I need to stop. But this is also, it works vice versa. So for example, if any of the servo drivers have a problem, say one of the input pins, say I've got an emergency stop, I've got an alarm, then it goes ahead, goes into this safety circuit system, and then in hardware it says, right, I've got a problem, I'm going to cut all the other servo drivers out. This works quite well in my application. The inputs and outputs are configurable. So I've done this through some jumper pins which are over here, but essentially the jumper pins allow me to choose which inputs and outputs I want to be part of this safety circuit. So if I want, say for example, my e-stop to be connected, I slam on my e-stop, okay, it then sends a signal to the safety circuit, it then pulls all of these pins low on here, which tells the servo drivers I've got a problem, and then it might maybe send a signal to some of the outputs over here. So in my instance, I've connected the output to my stepper driver, to my alarm on my stepper driver. I've also got an alarm coming in from my stepper driver, which comes in to this side of the safety circuit. And then in essence, the safety circuit is also connected to the motion control board. So if anything gets pulled low or high, depending if there's an emergency, it sends that signal back to this over here. It just gives me a little bit more control of the aspect of, well, some of the safety aspects on the system. It doesn't rely on the motion control board, and it doesn't rely on Mach 3 trying to, you know, look for those signals and then stop the motors. It stops the motors all by itself. So let me know in the comments, or I might put a poll below if you want me to manufacture some of these boards. Essentially, I've only manufactured one for myself. It works well in my application, but I guess the essence is to be a plug and play system between this motion control board and the cheap Chinese servo drivers. If people are interested in producing or wanting some of these boards, maybe I can manufacture a couple and then sell them on. One thing I would notice, or one thing I would note, is the onboard safety circuit that I've actually put on here. It adds another level of safety to, say, the motion control board, or say the e-stop that otherwise go into Mach 3. But it can't really be relied on as the main means of safety in an application. For that, you probably need to be cutting the power to the servo drives rather than sending an emergency stop signal, which, you know, puts the drives into emergency state mode. You need to be cutting the power to that, and maybe for that you might be using something like a Pilz relay or something similar to actually do that in your application. But this circuitry on here just adds another level of safety to the standalone e-stop that would otherwise go into Mach 3, but isn't a definitive means of controlling the safety in a system. So why have I decided to go for these servo drivers and motors? Well, it's because they're cheap. I mean, 3 servo drivers plus the motors plus the encoder cables, that's 1000 watts, 750 watts and 1.8 kilowatts. All of it cost me 800 quid. That's including postage, that's including tax. So I couldn't find anything remotely close in terms of price. The biggest disadvantage? Tuning. It's difficult to tune these motors, or it's difficult to tune these servo motors, because you don't really have access to see what those motion profiles look like. There's no auto tuning on these, and the algorithms that actually control, say, the closed feedback loop, they're maybe not as advanced as some of the better drivers out there. But for the price, you can't really complain. For my application, I'm getting usable parts out of them. I mean, I haven't measured the interpolation of circles. I haven't really measured, some of the parameters out of it, but I do know my parts, say, look good with the vernier. They look good with, say, a micrometer when I'm measuring lengths, distances, thickness, whatnot. So another thing with them is you have access to actually control them through a number of means. So for example, if I want to command it using pulse and position, I can do that. I can also command it using 0 to 10 volts. I can do that too. The inputs and outputs and actual servo drives themselves, they're configurable. So there's 4 inputs and there's 4 outputs. But you have a list of 27 inputs, or you have a list of 27 programmable parameters. Say for example, some of the programmable parameters on that one there, or on any of them, is to change between, say, torque mode and pulse and position mode, or position mode. So at a flick of a switch, you might be running this servo motor which controls my spindle. You might be running it in torque mode. I'd be like, well, actually, I want to run it in pulse and position. I want to do some rigid tapping. Flick that switch, and now it's looking at the pulse and direction signals coming in. So having that flexibility allows you to use them in more, more demanding applications. One thing I would note, or one thing I would say, is that motor there, that 1.8 kilowatt, didn't come with a braking resistor, so you might need to add your own braking resistor. The other two seem to come with the braking resistor. Other features that this has, it has electronic gearing. So say for example you're running a system that only runs 100 kilohertz, you want your maximum speed out of your motors. Well, you can actually go in here and you can change some of those parameters. So 100 kilohertz gives you your maximum speed. Of course, by doing that, you reduce the resolution, so you're not actually using those encoders to its maximum potential, but you are able to get your full speed. So it depends on the system, it depends on what you're setting up. For a servo system, for the price, I would say they're quite good. I mean, maybe one day I'll be able to connect the encoders up. I mean, I've already got the hardware all connected up to the breakout board, and it actually talks and everything. So maybe one day I'll be able to plot those motion profiles and actually look if I can tune some of these motors or these servo motors to get a better dynamic response. In essence, I'm pretty happy with what I've got here. They haven't been that difficult to actually hook up. I did actually have some problems, so I don't know whether, if you're following this in order, you probably haven't come across some of the problems I've had with the servo drivers. So I initially thought some of my problems, the problem effectively was jitter. So jitter in the motor. I would command a position and suddenly it would violently jitter. The actual problem didn't turn out to be anything to do with the breakout board or even the way that the pulse and direction signals were actually communicating to the actual servo driver. The actual problem was the fact that there's a default pin setting on the inputs that go into here. So you've got 4 inputs, and one of these inputs, so input 3, has a default setting which basically says clear the position that comes in. You switch it high and it clears the position. It turns out that actual pin, because it wasn't connected, maybe it was floating at one point, I'm not sure, maybe it was a dodgy connection, I'm not sure what was going on precisely, but it was causing the actual servo drive to suddenly just stop and then start and then stop and then start. When I went ahead and changed that, or in the case of my x-axis, what I've done is I've just made that pin high or stay high, the problem goes away. So problem's completely clear. So if you're having some registering problems, I'm going to post a quick video on that. Check that video out, it might help you. But otherwise, I'm pretty happy with these. So hopefully this video has been somewhat useful. There's not that much information about these servo drivers out there, but they are cheap and they do their job. It depends on what you want.